All right, hello IB students. In topic 27, we're just reviewing some basic probability. You might remember some of these topics from middle school, but that was a long time ago, so you just need a little review before we do some more advanced probability next class. So in the warm-up, you're just kind of trying to remember your background knowledge on probability and adding some words here that you remember. All right. First, we're going to talk about experimental probability. This happens when you do an experiment, like throwing dice. That's an experiment. In experiments involving chance, we use the following terms to talk about what we're doing and the results we obtain. So we talk about the number of trials, and that's the number of times the experiment is repeated. So in the dice throwing example, how many times did you throw the dice? The outcomes are the different results possible for one trial of the experiment. So in the dice example, the outcomes would be 1, 2, 3, 4, 5, 6. The frequency of a particular outcome is the number of times that outcome is observed. So if I rolled the dice 5 times and I got the number 3 twice, then the frequency of the number 3 would be 2. The relative frequency of an outcome is the frequency of that outcome expressed as a fraction or percentage of the total number of trials. So if I got 2 3s out of 5 trials, then the relative frequency is 2/5. Relative frequency is also exactly the same as experimental probability. So there's that. Here's another example. A small plastic cone was tossed into the air 279 times, and it fell on its side 183 times, and on its base 96 times. So there are 279 trials. The outcomes that are possible are just side and base, and they are 183 is the frequency of side, and 96 is the frequency of base. And then the relative frequencies are 183 out of 279, which to 3 sig figs is 0.656, or 96 over 279, 3 sig figs is 0.344. This means the probability it lands on its side. And there's your probability. This means the probability it lands on its base. Okay, here we have a table of information about the short-term visitors to Australia. The first one says, estimate the probability a person who visits in June is on holiday. So we know they visit in June, so we're only considering these people. And out of these people, the number who are on holiday is 156,500. So our relative frequency, or our experimental probability, is 156,500 out of all the people who traveled in June, and then you can get your 3 sig fig answer. Over here, this is the probability a person is on holiday. This line straight up and down means given that it's June. Estimate the probability a person who came to Australia in the period April through June arrived in May. So the probability of May is this many people who traveled in May divided by all of the people. So we had to add the totals for each month to get this number. Sorry, that was the number of people who were in May, and then that is the total of all of the people. The probability, let's see, Lars arrived in Australia in one of these months to visit his brother. So we know he was visiting family, so we're thinking about this line up here, visiting family. We want to know the probability he arrived in April. So this is the probability he arrived in April, given that he was visiting family. So April and family is 77,500. It's up here, 77,500. But then we know he's visiting family, so we don't divide by all of the people. We divide by the people visiting friends and family. So we had to add up these 3 numbers, and then that goes down here. And you should get this result. All right, two-way tables are tables which compare 2 categorical variables. For example, the teachers at a school were asked which mode of transport they used to travel to school. Their responses are summarized in the table below. So the teachers at the school were male and female, And then these were the modes of transportation that they used. Male and female transportation. And this is just an example of a two-way table. Over here is the one we're going to use for our next problem. People exiting a new ride were asked if they liked or disliked the ride, and the results are in this two-way table. So we have children who liked the ride, children who disliked the ride, which made a total of 72 children. 28 adults liked the ride, 30 adults disliked the ride, so that's a total of 58 adults, and altogether 130 people. So the probability that they liked the ride, we're going to add up the people who liked the ride and divide by the total people. The probability that they are a child and dislike the ride means they have to be both. They have to be a child and they dislike the ride. So there's 17 of them divided by all the people. When it's an adult or disliked the ride, it could be an adult only, it could be disliked only, or it could be both. It's and or. So let's look over here. The adults are 58. There are 58 adults. So I started with that number. And then there were also 17 children who disliked the ride. So I added all of the adults to the children who disliked the ride and then divided by all of the people. All right, the sample space, U, is the set of all possible outcomes of an experiment. It's called U because it's the universal set. An event is a set of outcomes in the sample space that have a specific property. Like maybe the property is that I roll a 3, or maybe the property is a student is wearing jeans. The sample space is the universal set U. The outcomes are the elements of the sample space. Events are subsets of the sample space. So we can list the outcomes in the sample space using set notation and then illustrate them in a Venn diagram. And we'll see an example of that really soon. Two events are complementary if exactly one of the events must occur. So often this would be the event A and the event not A. Two-dimensional grids and tree diagrams. So we're going to show you what a two-dimensional grid looks like, but those aren't used as much as the tree diagram, which is used often. Two-dimensional grid, tree diagram. Okay. So it says, let A be the event that a prime number is rolled. And so we're going to list the set event A, which is the prime numbers 2, 3, and 5. Not A is the numbers that are not prime numbers 1, 4, and 6. And then the sample space is all of the possible outcomes in set notation with these fancy brackets. To make a Venn diagram, you're going to have the rectangle for your universal set of all the outcomes, and then your event A will be in a circle. So event A are the prime numbers, and then out here is not A. All right, here is a two-dimensional grid showing you what can happen when you toss two coins. So here's coin 1 and coin 2. Coin 1 could be tails or heads. Coin 2 could be tails or heads. And so each of these intersections shows you what could happen. It could be tails, heads. It could be heads, heads. It could be tails, tails. Or it could be heads, tails. And here is your list of your outcomes. All right, we're going to show you the tree diagram for the spinner. It says the spinner is spun 3 times. So I forgot to say that this is the 3rd time here. So the first time, it could be blue or white. After you get that outcome of blue or white, again, the second time, it could be blue or white. It could be blue or white. And then the 3rd time, of course, after each of these, you have the possibility blue or white. So if you follow the tree, that shows you your possible outcomes. Blue, 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 white. Blue, white, blue, blue, white, white. White, blue, blue, white, blue, white, 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 blue, and white, white, white. So then the event blue exactly 2 times, you just pull out the ones that have blue exactly 2 times. Okay, that was experimental probability because you do an experiment and to see how often something happens. But you don't have to do an experiment all the time. Some things are very predictable. Like in the spinner, you know that each number is equally likely to land on. So we can talk also about the theoretical probability of something happening. Let's see. Since this spinner is symmetrical, we expect each of the 8 outcomes will be equally likely to occur. So the theoretical probability of any outcome is 1 in 8, or 1/8. If the sample space has n outcomes which are equally likely, then the outcome has a probability of 1 over n of occurring. So looking at the spinner above, of the 8 possible outcomes, the 4 outcomes 2, 3, 5, and 7 correspond to this event. So the probability of rolling this prime number or spinning this prime number is 4 in 8, 4/8, which of course simplifies to 1/2. So the probability of an event happening is the number of ways, the number of outcomes that correspond to A, divided by the total number of outcomes that you have. And the probability of something happening plus the probability of it not happening is always going to equal 1. A ticket is randomly selected from a basket with 3 green, 4 yellow, and 5 blue tickets. So to find the probability of a green ticket, you take the 3 green tickets and you divide by how many tickets there are. And then you want a simplified fraction or a decimal. A green or a yellow ticket. So this means or, it's the inclusive or, so it could be green or yellow or both, but we don't have any that are both. So green or yellow. And there were 7 that were green or yellow out of 12 altogether. None of the tickets were orange, so that's 0 out of 12. Green or yellow or blue, and that would be all of the tickets, so 12 out of 12, which is 1. Probability is 1. Okay, here's the 2-dimensional grid for tossing a coin and a die. So the die could be 1, 2, 3, 4, 5, 6. The coin could be heads or tails, and these are the 12 outcomes. The probability of tossing a head, so there were 6 ways you could get a head out of 12 outcomes altogether, which is 1/2. Tossing a tail and rolling a 5. So there's only one place where you have both a tail and a 5, so there's one way to do it out of 12 altogether. Tossing a tail or rolling a 5. So there are 6 tails, and we already counted that one, but there's one more 5 over here. So that's 7 altogether out of 12. Okay. Display the possible results when 2 dice are rolled and the scores are added together, and find the probability that the sum of the dice is 7. So on this 2-way grid, you're going to draw it, and you're just going to fill in the sums of all of these rolls. So 6 and 6 gives you 12. Like 1 and 1 gives you 1. 1 and 2 gives you 3, right? 1 and 1 gives you 2, my bad. But you're going to add them all up. When you do that, it's going to look like this. And you'll find that there are 6 7s out of 36 possibilities. So your probability is 1/6. Okay, down here, the universal set U is the children in the class. And the event B is a student has blue eyes. So you'll see 8 students have blue eyes. 15 do not have blue eyes. And that's 23 students altogether. So the probability of blue is 8 out of 23, and the probability of not blue, this little line means not, is 15 out of 23. All right, here we made a Venn diagram for this. So let's take a look. There's a class of 30 students, 19 study physics, 17 study chemistry, and 15 study both. So if you look at that, adding them up, that seems to be more than 30 students. And the problem is here that of the students who study physics, some of them are actually studying both. So we started by putting the 15 that study both in the middle, and then I know 4 more study physics and 2 more study chemistry. Now this adds up to 21 students altogether, but I know that there are 30, which means there are 9 out here. Now that you have your Venn diagram right, you can answer these problems. Notice the way I write each probability. This is the probability of physics and chemistry. So that's only the people who study both, 15 out of 30, 1/2. Physics, but not chemistry. So physics, yes, and not chemistry. So there's only 4 students there, and that makes 2 out of 15. Neither subjects, so not physics or chemistry. None of these, so these. 9 out of 30, which is 3/10. At least one, so that could be physics or chemistry or both. So physics or chemistry or both, 21 out of 30, which is 7/10. Exactly one of the subjects, so they could be physics and not chemistry, or chemistry and not physics. There are 6 students out of 30, which makes 1/5. So you can make predictions using probability. All you need to do is multiply the number of trials times the probability of each trial, and then you're going to round that to the nearest whole number in this case, because you can only make whole numbers of shots. So Michael Jordan made 83.53% of his shots, so we changed that to the decimal. He had 18 attempts, and so we multiply those, and we predict that he would make 15 of his shots. And that's it.